Hello, good morning. You're still muted, Maris. There
Here we go.
you go.
Coffee.
I know. Exactly. I woke up rather late today and I was like, you know what? Today's the day. I need some coffee. Like it'll be fine. How are you today?
I'm good.
Good.
How are
So what
you?
Oh, I'm fine. Enjoying it. So you enjoy the weather the past couple of days, hopefully?
Yeah, it was fun. So,
Good. Good. Well,
I'm
perfect. Well,
confused. Oh,
no, I was just gonna ask, what
sorry.
can I help you with? That's all.
I'm confused on number 6 for the practice
Practice
problems.
problems. Sweet. Let's do it.
I think it should be the same
Yeah, I
one because
think
like it matches. I think. I don't
scanning
know.
wave pattern established on a 246 centimeter long rope. Is it?
It's like you count 17 complete waves
Oh, yeah,
at
yeah,
a certain point. That one?
yeah. So
Okay.
it's that one. What is the velocity passing through these waves?
Yeah, it's that one.
Perfect. Let's do it. All
Thank
right.
you.
Of course. So let me get a whiteboard going and let's do it together. So that I'm gonna move you out of the way. Nice. All right. So the idea here is that whenever we're doing this, whenever we want to figure out like our specifics for it, what we're going to do is that on this problem, you need to first think about what are you trying to find? And for this, your end goal here is you're trying to find the velocity of this wave. So we could do this one of two ways. First off, you know that your velocity has two different equations right now. So velocity equals, and it's always going to be your wavelength times your frequency, or it could be that your velocity equals your wavelength divided by your period. It has to be one of those two equations. But let's see what we can do first to try and figure it out. So the very first thing is that we need to figure out a wavelength. No matter what, on either equation, there has to be a wavelength. And it gives us a hint by saying that there is 5.50 meters from a crest to a trough. So this distance here to here on this wave is this 5.50 meters. Well, the idea here is that part of this problem, as always, is knowing what exactly the wavelength's definition is. So let me ask you that first. What is the definition of a wavelength? Okay, so let me ask you this. What is wavelength talking about? Like if you just have to just, not like physics definition, but just like describe it to me. Like what's a wavelength? What's it do?
Is
What's
it
it?
the length of a wave?
Yeah, exactly. So let me ask you, what does a wave normally look like? A wave normally looks like, yeah, it's like boom, 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 boom. So if I draw, oh my gosh, that was horrible. But something that looks like that, how do I determine a wavelength based off of that horrible, horrible image?
Can't you like find the period of it then? Like, cause you can count it or something? No?
Wavelength,
Okay.
so period is an amount of time, remember? And wavelength is a distance. That's like asking how many feet are in 3 minutes. Like the two things are completely independent of each other. The idea here is that, okay, a wavelength always has to be from one spot to the exact same spot on a wave. So it has to be like a trough over to like a trough, or like the equilibrium spot over to the equilibrium spot. That's what tells you that it's a new wave. Think of it like a lap, almost on like a track. You know, you have to go around the track and it's only, here, let's see if I can't draw a track. Okay, not bad. So, you know, if you start here and you start running in that direction, you only get to one lap whenever you hit back in the exact same spot. It's the same thing with a wave. A wave has to go from one spot over to the exact same spot in order to have a perfect wavelength. So, ours right now is 5.50 meters from the crest to the trough. And we have to say, in order to get wavelength, we want it to the exact same spot. We want a crest to a crest.
So we just times it by 2 or something?
Exactly.
Yeah,
Exactly
okay.
right. This distance is also going to be 5.50 meters. So if we want our wavelength then 5.5 times 4 plus 5.5, 10, 11 should be 11.0 meters then for our wavelength. And that works out just fine. Now, we need to either find our frequency or we need to find our period. And thankfully, you know that the two of them are inverses of each other. So as soon as we find one, we find the other. So on our problem, it says you count 17 waves in 120 seconds. So if we have 17 waves in 120 seconds, here's the idea. First off, I'm going to get you again. What's a frequency? Let me start here. What's the unit for frequency?
Hertz.
It's hertz. Now, what does a hertz mean?
1/second, right?
Perfect. So it's 1/seconds. It's how many waves occur per second is a hertz. That's what it's really talking about. So how are we going to find the frequency if we have 100 or 17 waves in 120 seconds?
Would you like do 1 divided by 120 or like 1 divided by 17?
So you're on the right track. You're knowing we have to get this 120 to 1 is the idea, because hertz, 1 hertz is just 1/seconds. So by itself, if we want our 1/seconds, we need to get that 120 over 1. And to get 120 to 1, we just divide this by 120.
Oh.
Now, think of it this way. If we have 17 over 120 seconds, and we divide this by 120, what do we have to do to the top to get the same thing? We need to divide that by 120 also.
Okay.
And what that is going to give us is that if I pull out my handy dandy calculator, 17 divided by 120, I need 2 sig figs, should be 0.14 hertz. Or if you want to flip it, because you can always do period, is 1/frequency. And I don't like the 0.14 because that makes me annoyed. We could just turn it into 7.1 seconds. The idea here is that it takes 7.1 seconds for 1 wave to travel of wavelength 11 meters. So now if we want to solve for our velocity, I'm going to do the wavelength divided by the period, because 7.1 sounds a lot nicer to me than 0.14. But honestly, it would not matter. I have 11.0 meters divided by 7.1 seconds. And we are going to get, divided by 7.1, 1.55 with 2 sig figs should just be 1.5 meters per second. Yay. So it really is. Those are that's one of those questions that you're just trying to figure out, like the definition of each, knowing what a frequency is, knowing what a wavelength and everything. But that's okay. Now, I am going to tell you, I am going to be uploading all the videos to the questions later today. I'm going to make a big old YouTube video of all of them. So hopefully that'll help you out a little bit also if you're having some issues. But good morning, Zoe. How are you?
Good. How are you?
I'm good. I got you while you were drinking.
Oh, yeah.
All right. What can I help you with this morning?
Okay. Can I have help on like the lab and the quiz?
Got you. I got you.
So, like, when you say like we're just supposed to like play around, how do we know like exactly like how good it is. Like to know that it's like, I don't know, like not like wonky.
Not
Like
one.
I can kind of tell like when it's like not like wonky, but like for the laugh.
Uh-huh. Okay. Well, first off, let's do here. Do you see the lab on my screen now? Hopefully.
Yeah.
Perfect. Okay. To start out with, as I said, this lab, it doesn't have to be perfect. Standing waves and
Mhm.
harmonics are not perfect unless you have a perfect like tuner pitch on like a guitar or a piano. Like it's
Mhm.
not going to be absolutely fantastic. But the idea on the lab here is that, oh, well, that is one. Let's just make something weird. Whenever I try to figure out exactly like a standing wave, it's not going to have to, oh, no, never mind. I was like, as I go and create a perfect standing wave. But the idea here, can you tell me and describe to me, this isn't a perfect frequency for a standing wave? And let me ask you, why isn't this a perfect frequency for a standing wave?
Because it's too like small.
Well, okay. So a standing wave is going to create the largest amplitude. Absolutely, you are correct there.
Yeah.
A standing wave is called a standing wave just because it creates a really, really large amplitude. But a standing wave has to notice and has to be like standing still in the end in order to figure out exactly like what you're doing. Of here, do you notice if I even turn it into slow motion, that not every single wave function like is at the same time? You notice like how over here,
Yeah.
these are really small and it's kind of dying over time.
Mhm.
So I wouldn't call this a standing wave in the slightest. And you can tell that's just by the frequency of it's close,
Mhm.
but it's not great. So all I want you to do is, again, just play around with it. See what you can get. And we can say then, let me ask you, is this better or worse than the last frequency we had for a standing wave? What do you think?
Mm, better?
It is, absolutely. Do you notice how it's like staying longer, or each one of the specific spots is, even if I go into slow motion, it's kind of all moving at the same rate. But again, it's not
Mhm.
perfect. You can see this wave every time it oscillates. This wave function is still coming through and it will kill this wave in the end. So even here, it's not like fantastic, but it is better. So we know then that we need to keep on going up because I went from 230 to 235. So now let's try 240.
Mhm.
What do you think about this one?
That one's good.
I would agree with you. It's not like perfect because again, it can go and it can die, but it's definitely better than what you have. So in reality, you're just trying to play with it. Like it's not meant to be a perfect exact answer all the time, but you notice here, this is a much, much better standing wave than what we had in the past
Mhm.
just because of how it's moving. So if we pause this standing wave again, and we count the harmonics for it, you count the antinodes, you have 1, 2, 3, 4, 5, 6 antinodes on it. 6 points of high amplitude here. And that would make it the sixth harmonic. So I would write down for the sixth harmonic, the little square 6, that it has 6 antinodes. It has a frequency of 2.42 hertz. And then finally, it has 1, 2, 3, 4, and 5 nodes here.
Oh, are the notes the little green ones?
No. Nodes are points on like the equilibrium that don't move. So again, if I press start, you notice that there's points here in between the two ends that appear like they're not moving. So
Oh.
it's not necessarily even the green ones. The green ones, what they are, is that it's like meant to be like a certain distance away from each other.
Oh,
So,
okay.
but no, because it's always going to have the green ones. But no, if I, again, just turn it into slow motion, a node is a point of perfect destructive interference, meaning that it's always going to be along the equilibrium. Because that's what a standing wave is. It's a point of really, really like fantastic constructive and destructive interference at the same time. So that's kind of the idea. Now, something that I have seen is that students, I think, are getting confused on like the distance and trying to figure out the like wavelength of each one. And
Yeah.
to find the wavelength, that's why I have you take the length of the string at the very, very beginning. So if I just restart, pause, restart, and we want to figure out the length of this string, that's when I just move my ruler over. And again, this is in centimeters. Well,
I said 7.5/8.
Oh, don't you dare give me fractions. Give me a decimal, Zoe. So
No, like 7.5.
there we go. Yeah, I'll count some.
And then I put like a slash and then 8, like both. Like it could be both.
No. It's not.
Oh, okay.
Slash.
Then
7.5 centimeters sounds great to me. So if I
Okay.
go and I want to figure out like my specific, here, let's get rid of these. Clear all. If I want to figure out my specific wavelength, just remember my wavelength is always going to be 2 times the length divided by the harmonic. So for that specific one, that's the equation that I want you to know from standing waves. Wavelength is always just 2 times your length divided by n, and n equals your harmonic. So
Okay.
for that one, I think we were on what, the 6th harmonic, if I'm not mistaken. So your wavelength would be 2 times 7.5 centimeters, and then divided by 6. So
Okay.
2 times 7.5, that's 15. 15 divided by 6, so 3 and some change.
Wait, how did you do that so quick?
It's my job, isn't it, Zoe? Yeah. 2.5.
I know, but
So
oh.
2.5 centimeters is going to be your wavelength for the 6th harmonic. So
Okay.
that's the idea.
And then velocity, it's just the wavelength times f. The
Correct.
frequency?
Correct. Perfect.
Okay, so then it would be 2.5
Not
times 2.42.
What's up? So was our, you would have 2.5 centimeters times frequency, and our frequency was 2.42, you said?
Mm-hmm.
Yeah. So times 2.42 hertz. And in the end, 2.5 times 2.5-ish. 6.05.
Yeah.
Perfect. And that's just centimeters per second. So yeah, perfect. And you just keep on doing that for each harmonic is kind of the idea. Have you done your lab already, Maris? Do you think your lab turned out pretty nice? Are all of your velocities about the same, give or
No.
take?
Oh well.
Perfect. Because, I mean, again, that's a way, it's not like the way in which you know you're right, but it's a way that you can check. Is that if all of your velocities are around the same value, then you know you probably did it.
I mean, they're not great, but.
And it's not meant to be perfect either, like as I said, but that's okay.
Wait, I have a question on the practice problems again.
Of course.
So I just submitted my like quiz thing.
Mhm.
My Canvas said that it was like number 1 was wrong, and it said to like watch my sig figs.
Yes,
Mm-hmm.
because you probably have 500 seconds, correct?
Yeah.
How many sig figs are in 500 seconds?
Oh no, I forgot to count them.
Ow.
Sorry, it's been a while.
Yes, it has. 500 seconds. If we think there's no decimal, there's no nothing. This has 1.
This one. Right.
How many sig figs did you start out in that problem?
Like 1 or 2?
2.
2 maybe? 2?
Uh-huh.
Okay.
So you have to somehow turn 500 seconds into 2 sig figs. Your 500's right. I wholeheartedly agree, but it's just sig figs. So the 2 ways, again, I can't do it on the computer, but you could draw like a line over it. to do your last significant, or the thing that I did?
This is the 5.0, right?
Yeah, I turned it into scientific notation because right here, that gives you 2 sig figs. So that's the main idea with it, but it's not bad.
And then how would you do it for the 8.3 repeating?
Well, what's 8.3? I can change color. Yes. So 8.3333 all the way. How many, or what do you need in order to figure it out? It's still just 2 sig figs. So if you want 8.333, it's just 8.3. Because this one doesn't round up. So yeah, scratch all that out.
Okay then.
Yeah,
That makes sense. Okay, I'm done then.
no, it's confirmed unpracticed because we haven't been in a classroom for like, oh, what has it been? Almost a month now?
Jesus.
Yeah.
It's gonna be more than that. I was so excited to come back to school actually, and then they're like, "No, it's May now," and I was like, "Oh."
Yeah, May 3rd, I think, is our intended date now.
May 4th.
4th?
Yeah, because
I
it's
don't-
Star Wars. May the 4th be with you. I'm sorry.
Mm, that's a good way to remember it. Thank you. I like it.
So
I know.
Okay.
No, we got some time, but that's okay.
go. Right. Thank you.
Of course, Maris. See ya.
Bye.
Goodbye. Have a good one. All right, Zoe. So you think that you're doing all right? Do you have more questions for me, you think? You just want to
Yeah.
kind of... What's up?
I'm probably gonna stay on the whole time because
That's
I
fine.
just want to make sure. But for the first one, for the wavelength, I got 15. Is that right?
You should have divided by 1. Yeah. No, 15 centimeters. That's
Okay.
awesome.
And
Oh.
then I'm only missing 2, and I'm missing the number of anti nodes for 3, 5, and 7.
Okay.
So should I just like make the frequency for 7 like higher because all of them are like increasing?
You can. That's one of the ways.
Okay.
Now think of it this way. If you're trying to figure out the number of antinodes, what tells you the harmonic? It's always the number of antinodes. So do you notice, what's the number of antinodes for your first harmonic? Because you just said that you solved for that.
1.
1. What's the number of antinodes for your second harmonic?
I don't have that, but I'm guessing 2.
2. It's always
Okay.
the exact same thing all the way down. So even if you want to create like your 7th harmonic, which should be around like 2.8, and we try to create that standing wave. There we go. Then you can go and you can see immediately, oh, that's not perfect. No, it's definitely not perfect. Let's change it a little bit. But if you create your standing wave, there we go. That's better. And you can see again, it's always going to have the same number. So 1, 2, 3, 4, 5, 6, 7. This is like the 7th fret on a guitar. It's just the 7th harmonic off of the fundamental frequency. That's all.
Okay,
So-
that makes a lot more sense.
Yeah. So the number of antinodes always matches the harmonic, no matter what it is.
And then would the number of nodes be
So if you count it, it's 1, 2,
5?
3, 4, 5, and then 6. The number
Oh,
of
okay.
nodes is always 1 less than the number of antinodes. So if you have 7 antinodes, you're going to have 6 nodes. 6 antinodes, 5 nodes. It's always 1 less than your others.
So wait, then if I have 4 anti-nodes, then I would have 3 nodes?
Perfect.
Okay,
Perfect.
now this is starting to make sense.
Good. As I said, it takes a second. I know it's a difficult lab to do, especially whenever you don't have anything, right in front of you, but No,
Yeah.
it's always a lot more fun.
What about for predict the frequency of the 16th
So let me
harmonic?
ask you this. What's your frequency of your fundamental? What's the frequency of your first harmonic?
0.40.
Awesome. What's the frequency of your second one?
Don't have that one.
Okay. Let's do your frequency of like your third one then. What do you get?
Okay. 1.25 hertz.
Okay. So if we go 1.25 and 0.4, the idea here, let's do 1.25 divided by 3. If I do that,
Okay.
I get 0.41 for our like answer. If I do 0.4 divided by 1, then again, I'm going to get about 0.4. I want you to think, if I have around like 1.6 hertz for a frequency, what do you think you're going to get? How many nodes and antinodes, or which harmonic do you think you're going to get if it's around 1.6? What do you think?
4.
Perfect. And you notice it's a perfect 4 standing wave. What's the pattern that you're seeing in your lab right now? What does it go up by every single time? What frequency change does it have between like their first fundamental harmonic and your second? Let me ask you that.
Is it going up by 0.4?
That's exactly right. So with this string,
Yeah.
it's always 0.4 times your harmonic. So if I want to make the second harmonic, I would take 0.4 times 2, and I get 0.8. So if I change my frequency to around 0.8 and I restart it, I should get my second harmonic standing wave, which is what you see right here. It's the exact same thing. So how are you going to estimate the 16th harmonic? What are you going to multiply 16 by?
So it would be 16 times 0.4.
Perfect. It's always multiplied by your fundamental frequency, which is 0.4 hertz in this lab.
So 6.4 hertz.
Perfect. And I can't show you because it only goes up to 3, but that's the main idea. It's always times 0.4, whatever your value is. And again, it's not going to be perfect, but that's the main idea.
Mhm. And then what is the part where it says determine the accuracy?
Well, let's do it.
Is that
So-
where we have to like calculate like the, I don't know what it's called, but like do the percent thing
No, not in this one.
and
Normally,
find
normally you're right. You would have to do like a percent error. Here, let me just clear all this. But what we're going to do this time is that we're just going to figure it out. You figured out that your fundamental frequency immediately is that 0.4 hertz. So your
yeah.
fundamental is 0.4 hertz, give or take. The idea is that with that lab, it's not going to be perfect every single time. And what I mean by that is that if we take the fundamental of your fourth, what's the fundament or your frequency of your fourth harmonic in your lab? What'd you figure it out as?
1.61.
Perfect, 1.61 hertz. So what I'm asking you to do is I'm asking you to figure out how close you are. And what I mean by that is that if you're going to do the fundament or the frequency of the fourth divided by the frequency of your fundamental
Oh, so
first,
we just, okay.
you're going to do 1.61 divided by 0.4 hertz here, and then
And
hertz over here.
4025.
So 4.025. And that determines your accuracy. And what I mean by that is that you are 0.025% off your harmonic. That's all it is.
Okay.
So, and a 0.025% is like next to nothing, meaning you're doing your lab perfectly.
Okay. And then table. Oh gosh, okay. And then for the third, like the last one,
Mm-hmm.
the problem,
Yeah.
is that, oh, okay, that's
I'm just,
asking what
yeah.
the velocity, okay.
Yeah, I'm just changing around your variables. So I'm asking you to solve for this equation, velocity equals wavelength times frequency. Oop. And then you're going to go and you're just going to do your wavelength equals 2 times the length divided by the harmonic. So I'm just having you practice that equation, which is what I'm also having you do in like your practice problems over on the side. It's a standing waves equation. So I'm just hoping that you go and solve for a standing waves equation. That's all it is.
Wait, so Mr. Tate, did you get for the problem 131.352?
It sounds good, but check your sig figs as always.
3, so it would
Perfect.
just be 1.3.
Perfect. Good job.
Okay, I was just nervous that I was going to do something wrong for this lab and like
Oh, no. It's
mess it all up and give a 0. That's what
no,
I was nervous about.
no. There's no such thing as you messing up and getting a lab or a 0 on a lab. Like that's just not a thing, especially not in this day and age
Okay.
wherever we're communicating through screens. Like,
Yeah.
no. The only reason you would get a 0 is if you didn't like turn anything in for like a month-long period. But no, you're doing great, Zoe.
Yeah.
So
So then for the last problem, would I just figure out the velocity or do I have to find the wavelength too?
you have to find the wavelength. Like this is your last problem down here over on the side, and you have to find the wavelength first in order to figure out your velocity. Because this is the only equation, the one in pink, that you can solve for, is you have to say that your velocity equals your wavelength times your frequency, but you don't know, or you know a frequency. So what's your frequency there in that problem? Let me ask you.
31.2.
31.2 hertz. Awesome. And then you don't know your wavelength. And that's just
On the
because.
phone. My teacher, I'm doing a Zoom. Sorry, Mr. Tate.
You're fine. Don't worry in the slightest. So for your wavelength is always 2 times the length divided by the harmonic, whatever that value is. So if we take 2 times, and then what's your
2
length
times
there?
7.0. Oh, 2.4. 2 times 4.21. Okay, so 4.21 times 2.
Mm-hmm. And then what's your
8.42.
perfect? What's your harmonic?
3, the third one.
Awesome. So 8.42 meters divided by 3. Still keeping those 3 sig figs.
2.81.
Yep,
Because
perfect.
yeah. So then that's our wavelength, and now we do,
The velocity, exactly
Yeah.
right. 2.81 meters multiplied by 31.2 hertz. So 2.81 times 31.2, we get 87.67 with 3 sig figs, should be 87.7 meters per second. There we go.
okay.
That's the idea.
And then for the quiz,
Mm-hmm.
like how are we just supposed to like do the work and we can just put in our answer, or do we have
Correct.
to like, okay.
Nope. So I can't collect your work, as I said. We tried that with the formative
Yeah.
of showing your, and that, oh my gosh, no. And I want some way for you all to get instant feedback, which is why I made it like that multiple choice. But no, you try the work, you plug in your answer. If your answer is wrong or it doesn't match, then you just do it again. You have an
Okay.
infinite number of tries there. So everyone hopefully should be
Okay,
getting
good.
100% there. And you just
Okay.
keep on trying, keep on trying, keep on trying. As I said, I'm going to be posting the videos of me solving them because I had a couple of students asking for that just right after this. I'm going to go and make it and upload it to YouTube. So you can also check
Mhm.
there. But it's just meant for you to get more practice using those equations. That's all it is.
Okay. Uh, I think that's it.
Okay. I mean, of
Well,
course.
thank you so much, Mr. Tate.
I'm
That
always
helped a
happy.
lot.
Good. I'm always happy to. You know that. But go ahead, take a try. Enjoy the rest of your break. And
You
I guess I will
too.
see you next week. But see you, Zoe.
Bye, Mr. Tate.